Cyberhuman Frontiers, the place to be for lots of fun on Saturday nights, Eastern Time, 9 p.m. every week. How you doing, everybody? Thanks for joining us. Getting community guidelines out of the way real quickly here. The points of view and purpose of this video is not to incite fear, violence, or harass, bully in any way, but to share opinions and thoughts with other like-minded individuals curious about the subject, to encourage conversation and awareness. The opinions expressed on this stream belong solely to the persons expressing them and are not a representation of the channel, Cyberhuman Frontiers. The video in our channel may contain certain copyrighted works not specifically authorized, but which we believe in good faith are protected by federal law and the fair use doctrine for one or more of the reasons noted in the Copyright Act of 1976 listed below. We make it a regular practice to post links and give credit to the other content creators and lecturers for their fine presentations and articles, and tonight's episode is no exception. You will find links in the show notes below the video. And here we are. So tonight's subject is self-assembling biocompatible spions, or spions. So what's a spion? That stands for Superparamagnetic Iron Oxide Nanoparticle. So let's deconstruct that a little bit. Magnetic or paramagnetic, very much similar. Iron is a magnetic possessing element, and iron oxide is another form of that. And when we're talking about nano-sized particles, they're real small. And how may these be used? One good application, which is currently in development, it is precise targeting of delivery of drugs to specific areas. Now, how would it be facilitated by that paramagnetic capacity of the iron? Because if you apply a magnetic field, whether it be electromagnetically or with a permanent magnet or a focused conjunction of groups of electromagnetic fields, you can get concentration of particles that are sensitive to that energy, very much like what you'd see in a wavetable in a sand tray or in water. You can actually make these things concentrate in certain areas. But there are many other methods by which these spions could be used as well. By way of review, I would like to just start us off with, let's see here. I'm going to start us off with a little diagram. And this kind of tells you where we're going. Let me get this thing up for you. Please stand by just for a second. And, okay, see how that looks. All right, so what you're seeing on your screen is a version of a spion over on the left, these little dot things. So what you're going to find inside there is something that is a little bit more than just a nanoparticle that can be absorbed by a cell membrane. So over on the right, outlined in blue, we're seeing a kind of a graphical or illustrative depiction of a cell and what's in it. And there are various internal components that can be put into a lipid encapsulated nanoparticle. One is a piece of iron oxide nanoparticle. So various methods by which these things can get into a cell. And of course, the idea to get them into a cell is if you're carrying on board in one of these particles a tiny micro dose of some particular drug or a tiny piece of genetic code which has a destination to repair something in a cell, this is a way to get it in there. And because these things are superparamagnetic iron oxide nanoparticles, or spions, they have more capability to be steered and targeted to where you want to get them to. So there are three main methods by way of this artist's conception. We gave credit to who drew this graphic in our show notes as well. One is by, on approach to the cell membrane, this thing will depolarize an area of the cell membrane and it will allow it to be absorbed. Another method would be, if it is not particularly rejected by the cell membrane, it could by simple diffusion, by there being a higher concentration of these particles on the outside of the cell versus the inside of the cell, by the occasional natural movement of molecules. The molecules and atoms are always vibrating. By the occasional natural movement of atoms and molecules, certain higher concentration will tend to be attracted to an area of lower concentration of these things. That would be called diffusion. And the last method is a more active method, which is by active endocytosis. So when this thing, this little nanoparticle, which has been designed with something with an outer coating, and it would most likely be a lipid coating, which has a definite compatibility with the lipid membrane of a cell, then it would be readily absorbed, if not welcomed, into the cell, because it would kind of like just merge, just kind of melt into the outside of that cell wall and thereby get into the cell. Now, once these things are in there, I'm not going to go into too much more detail about this, but there are various various actions that could take place once this thing is inside the cell. It could have to do with getting all the way into the nucleus, which is this thing in the small blue oval, for the purpose of delivering a piece of genetic code. And that could either modify or do repair work on DNA. It could get into the mitochondria and do repair work. There's also genetic code in mitochondria. And it could, once again, these things could be used to help repair a malfunction in mitochondria and other various things that could be done here inside a cell. So I guess the takeaway from this diagram is a few different methods by which these spions could get into a cell. Yeah, there's TMC, more. What do you think?
Yeah, there's more. So you went through these methods. I want to add a few.
Okay.
And what they're forced mechanisms to open up the cell wall. So membrane depolarization, there's a variety of ways to do that. And that can be done chemically. It can also be done through the application of energy. And so you can look up some terms. It's sonoporation. And what that is that's agitation of a cell wall with sound waves, acoustic waves, to open up a pore, a proverbial pore in the cell so that you can add something to it. And they have irreversible sonoporation or reversible sonoporation. And the difference being one destroys and disrupts the cell membrane permanently, and the other allows it to go back to normal. And this is a big deal because sonoporation can be done, again, with the induction or application of ultrasound. In addition to sonoporation, there's also electroporation, which is the application of electric fields or electricity or voltage. Mm-hmm. Right? And then there's also magnetoporation, which is the application of a magnetic field to do exactly the same thing as I was describing before, where you're forcing a pore to open up. You're basically perforating the cell wall membrane temporarily or permanently based on the application and what it is you're trying to achieve. If you're targeting cancer,
if you permanently perforate it, isn't that going to cause everything that's in the cell to leak out unless you put a molecular cork in it?
Yeah, cell death, apoptosis. And that's applicable for cancer. Things like cancer, it's a perfect application.
Okay.
Right? And so a reversible poration is something that temporarily perforates, temporarily disrupts, but allows the cell to go back to normal where it has an inside and an outside.
Very interesting.
And the other piece I wanted to add to all of this, you're seeing iron oxide nanoparticles just floating around loosely inside of a cell. That's not for the sake of a diagram. It's fantastic.
Yeah, it's a simple diagram.
Yeah, that's not how this works in real life. Those would be very, very toxic to a cell. It would kill the cell. So biocompatible polymerization or wrapping an iron oxide nanoparticle in biocompatible compounds, maybe not a polymer, maybe some biologic material for a temporary period of time for these iron oxide nanoparticles to move around.
See what they've done down here? What they've done down here is they've taken those iron ions and they're actually radicals, and they've gotten them into this. And once again, this is diagrammatic, but this would isolate the rest of the cell from being damaged by those free iron radicals floating around in there.
Yeah, the takeaway that I get from that, that happens in your blood, and not with the nanoparticles, but the ionization of iron in your blood has everything to do with its ability to carry oxygen around in your system. Mm-hmm. And so when you start introducing things that want to repel or attract iron ions, you're literally messing with the molecular construction of your blood cells that ultimately impact the ability for your body to transfer oxygen around, move oxygen from point A to point B. So iron is a big deal, and iron oxide nanoparticles have been around for a very, very, very long time. They're getting much more sophisticated, and they're manufacturing techniques for iron oxide nanoparticles, as well as other paramagnetic nanoparticles, are fairly sophisticated now, such that they can be made readily, very cheaply, and they're put in quite a few things for medicinal purposes. So, anyway.
Interesting that in hemoglobin, which is inside red blood cells, there is an iron radical, an iron ion inside there.
Yeah.
And it has to be well isolated from the outside, otherwise it would do harm. But the presence of that iron atom in there is what attracts oxygen into the red blood cell and allows it to actually carry that oxygen from one place to another. So it has a use, but it's got to be kept inside an insulator, if you will.
You have to have the right iron charge, the right ionic iron charge for it to bond with the oxygen. Otherwise, you get weak bonds or you get no bonds. And that's the part where you could be breathing and taking air into your lungs, but the exchange that's occurring in your lungs to bring oxygen into your blood to give oxygen to the rest of your body, if the ionization charge is not proper, then the oxygen transfer won't happen.
Right. Has to be sufficient to pull and bind the bind the oxygen temporarily onto that hemoglobin.
It's got to be like a covalent bond, and then as it moves to wherever it's going, then the blood will change. It'll pick up another positive or negative charge, and it weakens that bond, and then oxygen can move around in the body. But that's a little more detail, I think, than what we want to talk about right now. So
I'm not sure that it's covalent. Covalent bonds are really strong, and it takes a lot to break them. It might be electrostatic. And honestly, we're not experts. We only do this work for entertainment purposes and to try and translate some very technical stuff. What did you say?
I said, now you're going to make me look.
Okay. Yeah, no, that's fine. That's what we do. But yeah, we do a kind of a combination of entertainment and information here, and it's all for the purpose of helping people to understand what some of these brilliant people work on. And they speak with really big words and really long technical terms and acronyms, and we work at translating all that to bring it down to something that's relevant to all of us here and now today. So anyway,
It's a double bond, 2 electrons. It's an ionic charge of +2 that's on the iron side, and then it forms a double bond involving 2 electrons with an oxygen, and that's how it's transported through the body.
Yep. Okay. So it's ionic. Ionic bonds are weaker than covalent bonds. Covalent bonds, you really need something serious to blow them apart. But ionic bonds are very convenient in biological structures because they're easy to make and easy to break. So it doesn't take a lot of energy to make cellular processes work. So that's what I got on that one. And I could go a little bit more into a little bit of other background because there's going to be, I'm predicting that at some point there's going to be some sort of a merger between some of the carbon nanofiber and nanotube technology and some of this, but I don't think we're there yet, and I don't think they're working on it yet. I could go into a little bit of background about that if you would like, TMC. Otherwise, we can press on forward. I will put up one, you know what I'll do? I'll put up just one little diagram here, and I won't necessarily play any videos, but let me just get this thing up here. It's kind of neat. I mean, this stuff, hopefully it amazes you as much as it amazes us. So you're looking at here, this is a 6-carbon ring, all right? And so carbon has a number of different ways that it can aggregate. Multiple carbon atoms can aggregate. So each one of these gray things is a carbon atom. And this is one of the forms that carbon can aggregate in, this 6-sided structure. And in nature, that's a very strong and very stable structure. But then you can take, if you will, a sheet, and this is how they make carbon nanotubes. You can take a sheet of this material and then roll it together and basically stitch this edge together with this edge. And when you do that, you've made a tube. And of course, naturally, they go further and they say, well, can we make bigger diameter tubes and smaller diameter tubes? And you guessed it, they can. And they're even now working at manufacturing tubes within a tube. So you see here a sideways look at that, and you see an edge, an end-on view of the small inner tube, the intermediate, and then the outer. So what can be done with this is it's fantastic. If they were able to get another atom in here without disrupting the strong structure of this nanotube, and they were able to accomplish, what did I get there? They were able to accomplish in other words, achieving some other biomolecular properties, perhaps for interaction with other cells or cellular processes. One thing to be noted is that carbon fibers and carbon nanotubes are highly conductive of electricity. They're very good conductors, they're flexible, and they're extremely strong. In the grand scheme of all of the different types of elements and materials that you can use to make things, these things are really strong and flexible and electrically conductive. So fascinating stuff. Going to move on and take us on a little bit of a trip here into and this is just general stuff about nanotechnology. And one little thing that I ran across just today, and it's thanks to one of our contributors who's out there in our chat with us right now, and thanks so much for that. Take a look at what can be done with tiny, tiny little designed devices, little designed machines. And at Johns Hopkins, they're building something that now has, by way of altering the temperature and other energy input into this thing, what this will do is it will latch onto cellular structures inside the host's intestine. I'm going to show you the size of these. They're very small. And they call this thing a Theragrippers. The Theragrippers being about the size of a speck of dust, and that cotton swab contains dozens of those tiny devices. So on the grand scheme of nanoparticles, it's kind of large, but it's still real small. So the idea of this thing is gradual or extended release of a drug can be done by way of bringing in some of these design particles that have a tiny, tiny, tiny microdose of a drug in them. And what they do by ingestion is they will latch onto the intestinal walls. They look like this. And then over time, when the Theragrippers is exposed to internal body temperature, it closes. In other words, it latches onto the intestinal wall. And in the center of the Theragrippers, right in here, is a space for a small dose of a drug. So this thing, they've actually put a size scale here. This is 50 microns. So really fascinating. Now, relative to everything that we're talking about, these are actually quite large, but they're still small. And the same idea of building tinier and tinier technology and little machines applies with things that are much smaller, which we'll be talking about.
How many of those micron-sized devices could fit in a standard gel capsule for a pharmaceutical, like, let's say, blood thinner medication?
Billions of these inside a gel cap.
Yeah,
you fit billions of these little guys. They're only 50 microns. They're super tiny. So, and the mechanism that they have designed for these things is fascinating. Once again, this is research, cutting edge research at Johns Hopkins. So when the paraffin wax coating on the grippers reaches the temperature inside the body, the device automatically closes and clamps onto the colon wall. The closing action causes this tiny 6-pointed device to dig into the mucosa, which is the inner surface of the intestine, and remain attached to the colon, where they are retained. And then the release of the medicine payload gradually goes into the body. So if you can imagine other things at maybe an even smaller scale, or things that are not necessarily ingested and aggregate on the inner wall of an intestine, but things that can be put into the bloodstream and can be steered from one location to another and have a targeted area where they're destined to go, and then do something very similar to this And it could be so small that they are intracellular. And so, and anyway, continuing, the device is retained and release their medicine payload gradually into the body. And a little bit of prose here from the person that wrote this article. We've seen the introduction of dynamic microfabricated smart devices that can be controlled by electrical or chemical signals. These grippers are so small that batteries, antennas, and other components wouldn't fit on them. But guess what? The genius is in the design, because at the chemical level, this thing will basically curl up when it reaches a certain temperature. It's that at a atomic and molecular level, this has been designed to do a certain thing based on the ambient temperature. So you didn't need batteries on board. It's been built that way. So when we build things that can almost be, if you will, passive in how they're going to go about their mechanical function just by picking up on the energy around them, whether it be electromagnetics or temperature or chemical input of energy. That's really kind of where we're going. So anyway, Theragrippers don't rely on electricity or on wireless signals or external controls. They operate like small compressed springs with a temperature-triggered coating on the device that releases the stored energy automatically, autonomously at body temperature. So anyway, just thought you might find that interesting, little things like that. I got just another view of kind of what we're looking at. You are looking at, this is another diagram of a cell wall. This thing lined up right here, this is the fat boundary, the lipid membrane of a cell right here, okay? And what you're seeing is a designed particle that has little protein probes sticking out of it that have an affinity to be able to mate or bond or bind in a kind of a copacetic way to the cell membrane. So this thing will approach the cell, it will attach to the cell, and then its little port will open up, and then whatever the payload was that was inside this will be released into the cell. And that's not exactly the same, but it is somewhat analogous to this diagram right here. So if you can put all these pieces together, they're kind of all working. It's slightly different technologies, kind of all working in the same direction. What we're trying to do, especially lately for entertainment purposes, is to bring everybody to an understanding of how there is research going on at many institutions and industry for the purpose of getting intelligent control and modifying components into cells for the purpose of altering, modifying, or controlling, and even, if you will, remote controlling cells and cellular processes. We've looked at it with neurons. We're looking at it with cells. We got a picture of one that's got, DNA damage. We're going to transport in some RNA or DNA into this, then hopefully splice it in the nucleus and fix that. So many different ways that various people in various institutions are working to get in and accomplish that goal. As for why they're doing it, and as for what the potential benefits of it are, we leave that up to you. That's the part where where it actually it helps to promote your thought and our exploration further into the subject, which is what we kind of do every week. So that's what I got so far.
Is it my turn?
If you want. I have a 2-minute video. I have a little 2-minute video. It's not long.
Yeah, go for it.
You want to look at that?
Because when I'm gonna.
Okay, so you get ready. I got. This is very short, and we do have the link to this in our show notes. Hang on one second, and we'll get it right up for you. All right, let's see how that looks. Let's get that thing centered and make it look good. And I'm sure that the audio is going to play just fine for you. So we have here is title being Iron Oxide Nanoparticle Surface Modification, Synthesis and Characterization by Richard Hoff. Richard E. Hoff, you've got the thing there. And anyway, start by taking a look at this diagram right here before I even play it. We have an iron oxide nanoparticle. We have various things on the coating on the outside of this, and he's going to explain it to us. So without me talking anymore, I'm just going to go ahead and play it. It really isn't very long. Here we go.
Hello, my name is Richard Hoff. In this presentation, I will be discussing my research on iron oxide nanoparticles conducted in Dr. Wanse's lab at Temple University. Magnetite nanoparticles are materials that are suitable for a variety of biomedical applications, including contrast agents, targeted drug delivery, and tissue repair. Each of these particles possesses a single magnetic domain due to their size.
He's going so fast. I'm going to pause this once in a while here. He's doing a good job. So, ferromagnetism, ferrimagnetism, and superparamagnetism. Keep those words in mind. We'll be referring again.
Meaning that they do not possess a magnetic memory and can be utilized for in vivo applications using a magnetic field without the risk of aggregation in the blood vessels.
That's an important point. When you have something that once you magnetize it, that it holds onto that magnetism, if you ever took a common nail and a magnet, and you rubbed the magnet on the nail about 100 times, and then you found that the nail became magnetic. Well, that's what these don't do. They don't retain the magnetism. So if you magnetize them, they hold on to it for the time during which you're influencing them with the external magnetic field, and then they do what you want them to do. And then when you cease the magnetic field input, they are no longer magnetic. And that's kind of good, because if the other thing would result in them getting out of control and aggregating into these big clumps, and you'd have a problem.
I contributed to a study published in Nanomaterials that was focused on evaluating the toxic potential of these nanoparticles by utilizing neural cell lines. In my thesis, I also sought to establish a viable set of methods for repairing these nanoparticles and modifying their surfaces for enhanced delivery to cells.
That's important. All right. So he started out by looking at toxicity, and then he said, okay, we don't want to kill the cell. We got to kind of encapsulate this thing in something so that it can be biocompatible and even cell assimilatable. And these little things sticking out the sides of this thing, first he put a coating around the iron so that it would not be active, as we referred to earlier today. And then he added other little components, these little things sticking out. That is what helps to give it an affinity for a particular type of cell. We go on. He's half done already.
The nanoparticles were prepared using a method called hydrothermal synthesis, which involves the process of subjecting a high-temperature aqueous solution to high vapor pressure. This method has the advantage of a high % yield and provides effective particle shape and size control.
You notice how he's the very well-trained scientist who's really knee-deep in how you make these things. We can actually skip over this part, because when he talks about the actual chemical stuff, unless you're an organic chemist, you don't need to know this stuff. The big takeaway is that they're made, how you make them, and that they can do the desired result when you get them where you want them.
Functionalizing the purified particle surfaces with silane agents and organic molecules is important for the application-based design of nanomaterials. Preventing oxidation, increasing stability, minimizing aggregation, and improving delivery to cells. Using different particle characterization techniques, our group was able to evaluate the particle's material properties and toxicity before and after silane functionalization. We observed that large aggregates of nanoparticles predominated the samples, and individual particles can be observed after ultrasonication. We also observed that these particles exhibited subtle differences in toxicity to different cell types before and after functionalization. I was able to demonstrate that using zeta potential analysis...
Man, he's going so fast, but he's really good. I'm just going to back this thing up 5 seconds. There was a diagram.
I was...
Right there. Okay? So, notice that there are boundaries created inside a nanoparticle based on charge. And the charge is going to be based on what the atom and components are. It's basically layering. And this is all done by design. None of this, maybe things like this occur in nature, but these are basically kind of reverse engineering how nature works and then making something that is a purpose-designed little machine. And he's got 30 seconds left.
able to demonstrate that using zeta potential analysis and spectroscopy is effective for evaluating changes in the particle surface properties facilitated by the silane coating process. Future studies can focus more on conjugating cell-penetrating peptides to the particle surface.
Cell-penetrating peptides. Okay, there you go. Yep, very interesting. And he's going to finish.
I want to add something here.
Yeah. Oh, could you talk a little louder? I could barely hear you.
Yeah, is that better?
Nope.
Interesting.
Okay. There, you're getting better now.
All right. Well, I want to note here that what you're seeing on the outside, the H's and the O's, those are oxygens and hydrogens.
Yep.
And these are very common things that the body uses all the time. All the time. And so what they're really doing there is what they're doing is they're regulating the charge potential of this construction apparatus, whatever you want to call it, this nanotech. And that way it doesn't immediately bond with something when it goes in the body. You deliver it where it's ionically stable, so it doesn't have an immediate attraction to much of anything. And then at that point, it can be moved around wherever it needs to go. And then the bonds that you see there, the H's and the O's, those can start going away at a later time. And that's remote triggering mechanisms. Anyway, go ahead.
It's a nice diagram. Nice diagram. As I look at it, it kind of makes sense to me. And as you look at it, one of the big takeaways from this is this little peptide thing right here. That is the part that helps this thing to become not only compatible and non-toxic, but absorbable into or through a cell membrane. Right there. That's what helps it to do that. And then the silane coating, as he referred to it, is a coating that protects everything in the organism from whatever you've put inside of this thing. So anyway, and that's pretty much all he's got. Right
and evaluating their uptake into cells. For more information, please consult the references that I have included here. Hello, my name is Richard Hoff. In this presentation, I will be...
There you go. And so all very interesting stuff. All right, what do you got? I have more if you don't want to go.
I have lots of stuff. It's just
all right.
A matter of, where you want to keep going down this trajectory. Because the stuff I have, Indy, it's patents they're medical patents that discuss delivering paramagnetic nanoparticles to the brain for medicinal purposes. Epilepsy, Alzheimer's, like literally artificial neural control of brain circuits.
I think one of the places that we're going to go, if you have it lined up, is into this, which is method and apparatus for stimulation of biological tissue. But that might be later on. We might not get to this right away.
That is related to remember the mouse videos we looked at last week?
Yes.
So what you're looking at, I believe, is an MIT patent that discusses being able to apply directed currents and then steer the currents around. And yeah.
Why don't we turn this?
We may not.
Why don't we turn it over in your direction for a while and carry us where you will. Fearless navigator of the show, and we'll definitely come back to that one.
Okay, I will start here. So if you want this spreadsheet, this is a working document that relates to a lot of the material we look at on the show, and this is free. It's free information, so grab it. It's at the top of Human Internet One on Twitter. There's a link there. You can just grab it, download it, look at these things if you want. And what I want to share with you first is this document that's really going to, I think, set the table for a few different shows.
Yeah,
Andy.
Good place to start. Yep. Mm-hmm.
This is DARPA and the Brain Initiative, and this has been ongoing for a while now. And what it says here is that the White House, during the Obama administration, announced the Brain Initiative back in 2013. And it's supported by many, many, many different federal agencies, schools, corporations, and private interests, if you will. And so the different programs that DARPA is being public about as it relates to their involvement, participation, et cetera, with the BRAIN Initiative are as follows. And these are different programs that are designed to interface with the brain and the nervous system. And this is not a complete list. They left some of them out, quite frankly. And so the Electrics program is designed to interface with the nervous system and the organs systems to apply electromodulation to cells and tissues, etc. I'm going to see if we can get something that's got a pretty color. Yeah, this is a great one. So the haptics program starts to work, right, to provide, in this case, prosthetic hands. This is just an example. And so what you see here is a prosthetic, right? And you have an interface, the yellow and the red. And what you have down here is sensor / stimulator that's tied into the remaining tissue right after an amputation. And that interfaces with obviously something like Bluetooth or some type of a wireless connection. And ultimately this creates the bidirectional interface that connects to the brain to power and deal with this hand. And so this is where it gets into parts and pieces. Haptics program may in fact only deal with electrodes down here at the bottom, where you have a read and a write down here that talks to the computer chip, but then that computer chip then talks to the computer. It doesn't necessarily go directly to the brain. And what I want to sort of frame here is when we look at these programs, as we move forward in time, going through this stuff, understanding the automation of the human, we've got to figure out how to keep an open mind and see that these things overlap and interlace and can create completely dynamic closed loop systems directly to the brain out to your appendages, head, shoulders, knees, and toes, hands, feet, all of it, and complete sensory feedback. This is the goal of these types of programs. And in this case, this is a DARPA haptics program, which is directly dealing with amputations, et cetera, that allow for electronics to be applied into muscles and nerves at the extremities. This is another one. It's the hand I can never say this word, proprioception and touch interfaces, part of haptics.
Proprio something.
Yeah, what it is it's the knowledge of the orientation of your hand, for example, in three-dimensional space. So an example, you're cooking dinner, you have a phone to your ear, and you have a child tugging at your leg. You have a hot stove and a hot pot of whatever on the stove, and you're stirring that, talking on the phone, and you have a kid, hanging on your leg. The spatial awareness, knowing where your hands are, dealing with the oven or the stove, and the phone, and having an awareness of what your child's doing while they're in a potentially hazardous situation with you cooking on the stove, right? But you might be there all by yourself. There's nothing you could do. It's the best place maybe for them at the time, because at least then you have eyes on, you know where they are. So this idea of proprioception, or whatever that word is, it's this
I think it's proprioception.
That is it, brother. That's it right there. Proprioception. The idea of proprioception is the awareness of your meat suit in three-dimensional space and time. That's all that is. And
yep.
And your brain, there are signatures for that in your brain. When you're, for lack of a better term, subconsciously reaching for something while you're doing something else, and you're reaching back behind you and you want to grab something, for example, just that secondary, seeming like you're not even thinking about it, kind of an action has unique signatures in the brain. And it's a very interesting thing to study, because if you're able to modulate and regulate somebody's three-dimensional spatial awareness, the opportunities open up to do things like correct vertigo, or to orient a soldier if they get disoriented in a not so solid environment. So let's say underneath, in an avalanche, or in the water, or whatever, right? There's a lot of interesting things that can be done. with that kind of technology. So the next one down here is neural engineering and systems design. And here's the implantable brain chip, right? Implantable neural interface able to provide unprecedented signal resolution and data transfer bandwidth between the brain and the digital world. So you can see how these things are or may be tied together. Another one, NeuroFast, seeks to enable unprecedented visualization and decoding of brain activity to better characterize and mitigate threats to the human brain, sure, as well as facilitate development of brain-in-the-loop systems. Brain-in-the-loop systems. What does that mean?
To accelerate and improve, augment, or supplement functional behaviors, or to modify functional behaviors, or to inhibit certain functional behaviors. Right. You got to add words, and you got to extrapolate a little bit because it's all part of the whole picture.
Right. Well, there's different colors in the proverbial spectrum of how this is going to be expressed, this technology. Yeah. Once the technology is understood well enough, then it's a matter of finding the appropriate applications to use the technology. And that's the variety of the palette of color, so to speak, with respect to how these technologies are going to be expressed.
Once the technology has matured, it becomes a matter of choice and whose choice it is to do what with it that they want to achieve. To who or with who.
Right. So the program's developed what they call clarity, and what they're saying here is a revolutionary tissue preservation method, and it builds off recent discoveries in genetics, optical recordings, and brain-computer interfaces.
Man, there's such a mouthful in that phrase.
This right here, revolutionary tissue preservation, is a real fancy way of saying tissue re-engineering. That's what that is. Tissue preservation means you have to develop the technologies to regrow and reform tissue. If you can do that, and you can do that in a healthy brain just as you can in a damaged one. And what that is tissue and neural circuit re-engineering, rewiring the brain with physical manipulations with things like genetics.
And not just brain, it could be regenerating for example, it could be regenerating a thyroid or something or whatever, or a pancreas.
Yeah, but with respect to this program, the nervous system and the brain, we're there in that field. But Indy, you're absolutely right. I mean, that's the beauty of DARPA, is that through the trials and the efforts, there's going to be a lot of things that are learned but aren't necessarily considered applicable to defining success with the program objectives. That doesn't mean that whatever's learned is not valuable. It'll cross-apply, as you said, in something like tissue engineering of a thyroid.
If they get this to maturity and then to apply some of the same techniques of creating some sort of a scaffold that emulates what the structure of some organ should be, then it's really not going to be a big stretch to help grow a kidney, to regrow a kidney, a pancreas, maybe even a liver. Who knows?
Heart comes to mind. Lungs and diaphragm being hybridized, so to speak, comes to mind.
Yeah.
Bladder incontinence would be another beautiful app. Like dude, for older women who've they've gone through their childbearing years and whatever, right? A lot of people have issues. So do guys, for that matter. This kind of technology that we're talking about really provides an opportunity to dramatically improve quality of life during the last few decades of your life.
It's often not so much the bladder as it is the thing that the sphincter that's at the ends of it to keep it under control. The muscles get weak.
That's right. And so the idea of picking out the little gems or jewels from these programs, even though they're not directly applicable to something like a brain-computer interface, they open up opportunities for learning and for further exploration in other areas to do things that historically never been done, at least what we understand as history. I mean, you imagine, you're that old and you're done with depends. You're sick of it. So you can go pay some amount of money to go basically rejuvenate
those muscles.
Yeah. And turn the clock back, so to speak, 30 years on something like your like you said, the sphincters. Same is true for your heart. Can you imagine what that would do for people? Like if you were to, 50-year-old go in and the doctor finally, hey man, you're getting some plaque buildup and your blood pressure's a little high. Instead of taking blood thinners that's going to literally melt the fat out of your brain. Those of you that take statins and heart medication and blood thinners and stuff, anything that's going to regulate fat and cholesterol attacks your brain. Your brain's 70% fat.
Mm-hmm.
So if new techniques come online that are able to offer somebody proverbial age reversal in something like their heart muscle, the way that would cascade through the rest of their life, if they took that seriously, would be enormous, because then they can go out and they can stress their younger heart, which means that the muscles that they have an opportunity to get stronger. So does their cardiovascular system. So does everything else. So there's a lot of good things on the horizon if we get that far.
Fantastic things.
Yeah. We've been through the next gen non-surgical program. That's the DARPA N3 program. We're going to talk a little bit about that today in the context of looking at paramagnetic nanoparticle patents to show you how they deliver them into the brain and the body. And it can be done in a variety of ways. I'll show you soon. You have others. Reliable neural interface technology. And this program seeks to develop technologies to reliably extract information from the nervous system and to do so at a scale and a rate necessary to control complex machines. You mean like a meat suit, like a human? Such as a high-performance prosthetic limb. Okay. And we have this program. This one we're going to talk about in great detail, looking at some HRL laboratory patents. This is the RAM program, Restoring Active Memory. And this program aims to develop and test wireless, fully implantable neural interface medical devices for human clinical use. The device would facilitate the formation of new memories and the retrieval of existing memories in individuals who have lost these capacities as a result of traumatic brain injuries or neurological diseases. Now, imagine what kind of fun, statecraft would have going to something like the G7 or the G20 and proverbially pooping in the punch bowl with some of this cool nanotech that we're going to look at. And then all of a sudden be able to do something like form new memories or retrieve existing ones, meaning read a world leader's brain while they're dreaming, for example, with some advanced nanotech that interfaces with backscatter electromagnetic radiation that could be picked up without ever transmitting a pulse of energy, which means that you're silent and covert. Anyway, let's move on. Restoring Active Memory, RAM replay. This investigates the role of neural replay in the formation and recall of memories with the goal of helping individuals better remember specific episodic events and learned skills. An HRL laboratory, Hughes Research Laboratory, which is owned by General Motors and Boeing, have an immense amount of intellectual property pertaining to stimulating your brain and reading your brain while you're training, and then stimulating your brain and reading your brain while you're sleeping, so that you reinforce that learning and accelerate upwards of 30 to 50% uptake and retention of new information for like fighter pilots, for example.
Or any kind of knowledge for that matter.
They list a fighter pilot or a pilot in their patent applications. Obviously, their business model is to develop technologies and then basically sell or lease out their intellectual property to other people, other organizations, to then bring something to market for use. And their primary customers, HRL laboratories, mind you, owned by Boeing and GM, primary customers are going to be the military. They're going to be groups like SpaceX and NASA. It's going to be high-level government stuff. And when it passes through the classified section and goes to declassified, now you open up opportunities for high-performing people like executives to start using these things to give them an extra edge, where they maybe won't have to sleep for 2 days because they're traveling around trying to sell something, you know. There's a lot of interesting applications when you start looking at uploading and downloading information in and out of the brain. And that's literally what we're looking at here, is being able to upload and download information out of the brain.
Yeah, and in an overall sense, just revolutionizing the way that learning takes place.
Right. Exactly right. Revolutionizing prosthetics. And if you can look at DARPA and prosthetics and get an idea of what that is, what they're disclosing at this point is a plug that's on top of someone's head that's got an electrode attached into some part of the brain, and they're saying that that's cutting edge, and it's not. It's really not. That's very, very old technology. But that's the stuff they're showing the public to illustrate what the trajectory is. They're just not really being forthright with the speed with which that trajectory is being thrust and how far along they are. They're way beyond what they're telling the general public, in my opinion. Systems-based.
Definitely.
Yeah. Subnets. This program seeks to create implanted, closed-loop diagnostic and therapeutic systems for treating neuropsychological illness. Now, the implications of that are huge, because
That's interesting, because it can be standalone, closed loop,
yes,
and it's implanted.
Yes.
Doesn't have to be connected to the outside.
That's right. So a crazy way the futuristic version of that, right? Nanotech in the brain, genetic engineering in the brain, whatever, into the nervous system to be able to read and write. Over a period of time, you would be connected, and some of the time you may not be. During those periods of time where you're not connected to the network, like in your body, brain, nervous system.
Standalone operation, operating autonomously.
Right, enough information will have been grooved into your brain with some of these other programs, so that the brain will basically self-soothe and self-regulate when not under some type of a cloud-based, internet-based stimuli. And the easiest way to sort of imagine that is the Pavlov's dogs, where he rings a bell and he feeds them, and he rings a bell and he feeds him, and he rings a bell and he feeds him, and pretty soon he rings a bell, but he doesn't feed them, and they salivate because they're expectant of food. A Pavlovian response, right? That is more or less what I see with closed-based systems that don't have miniaturized storage devices. Now, that
and in reality, I can't really see them, if they get it this far, I can't see them making it completely closed loop. They're always going to want to have a back door or an outside connection. IARPA
has a program called MIST, M-I-S-T. And what that program is designed to do is take a data center the size of 3 football fields and take all of that data and compress it into the size of a wet bar fridge in a hotel that has DNA in it.
Yep.
And so the point is this: genetic information can be useful. You can encode genetic information, and that information can be delivered in the forms of a proverbial 1 and a 0, an off or an on in biologic code.
There might be a speed issue, all right? The seek time to pull that information, to actually go through the whole index of the entire DNA library, which is the equivalent of a whole bunch of hard drives.
That's not how the immune system works. The immune system sees a threat, and with very, very quickly it finds what it needs, and it starts producing antibodies or whatever it needs to fix itself. The pie in the sky future space age BS is networking up your DNA with nanotechnology that talks to the cloud, that allows for a closed loop system to work when you're not connected, that will allow you to function as if you were connected for some period of time. And in order to do that and miniaturize it and not have the body reject it and have it be upgradable and modular and all of that, it's going to be with the DNA. And the DNA will be stored in things like proteins. So a software patch for biologic code at this point is a proverbial, we're going to give you a new protein, a new compound, which is just a fancy way of saying a string of DNA that's been folded on itself to make something, and it's a protein.
Mm-hmm.
And if you could talk to that and have some of these other technologies where you're able to decode the entire brain structure, the entire resonance structure of somebody's thought process, understand their nervous system, be able to decode that, and then talk to it. The next step is to encode instructions in biologic material, aka proteins, and have that start governing or being the operating system. And we've heard that term before.
We have.
Operating system in the body.
Yep. Some of these engineers have talked about it specifically.
So that's Subnets is a very interesting program because it's more or less DARPA's version of the software side. IARPA, the Intelligence Advanced Research Projects Agency, right? They are very, very interested in software-oriented tool sets. DARPA is more interested in the hardware, but DARPA does work in the software space. But to really understand the software piece of advanced technologies that function with no contact, directed energy systems, satellites, cell towers, cell phones, whatever, the software piece, a lot more information is available when you start looking at IARPA.
It's interesting to step back and look at the way the body is designed au natural, without anything artificial. What we have really is a whole lot of decentralized little processing units. Even cells that aren't part of the brain, they're still doing processing, yet they are all networked, and they all share a whole lot of exactly the same code. So they all share a common library, give or take a little bit, and they're networked. And so this is kind of a, it's a kind of, once again, it's a merger between technology and what's already built into the way that we're put together.
Yeah, it's a hybridization. I mean, that's really what's happening. That's really the objective, I think, is to hybridize biology and silicon. What we understand is silicon, even though that's not mutually exclusive to that element. But we understand silicon as like the computer age, because Silicon Valley and all this, and that's an American thing. But it's
hybridize the human body with
right.
Man-made data processing and storage.
Hybridizing the human body with a digital interface. That's the hybridization. The hybridization is creating a digital interface in a biologic that functions on the internet like a cell phone, or functions on the internet like a Tesla car. It's probably more applicable, because a car actually moves around and does stuff. A phone pretty much doesn't do anything unless you're doing something with it, right?
Not to get so far off the beaten path, but it sort of scares me a little bit, but it also makes me just wonder why so much energy and effort and money put into this when there are spiritual methods by which people can seek to normalize whatever processes, body, mind, and spirit there are that are out of balance. And that is what a lot of people would identify as part of the journey of life, is to learn oneself and to self-discover, become more aware, and to influence one's physical condition, mental condition, psychological condition, and spiritual condition, all under one's own processes without having something go in like a big wrench and just flip switches. You know what I mean?
Yeah, well,
it's different. It's a whole different approach.
You do know that a lot of world leaders, if you were to, give them a diagnosis, they're either a sociopath or a psychopath, right?
Yeah.
So
true that.
Just saying. So
the thing is, a lot of them are the people who are at the levers of control of the money to make the cash flow to make this stuff happen. So they're looking at all of this through their lens, which I think might be a little bit limited. Maybe we can help them.
No, brother.
He says no.
So all of the beautiful, fluffy, colorful, hippie crap that you just said, which is all wonderful stuff, and I agree with it, right?
Don't brush it off. That's real.
I know, and I'm not brushing it off. I'm kind of making light of it because of what I'm about to say.
Okay.
That is very, very valuable. It's valuable to have a connection like that, and it's the ability for a human to be imaginative and to have inspiration and to be creative that is lacking with AI.
Yes.
And is lacking with complex computation. So being able to jack into a person and tap into their 12-watt brain and have access to all of their creative energy, to all of their physical energy, to all of their inspiration, to potentially their connection with the spirit world, dude, I mean, if you could latch on to every human and be able to extract that at will from every human, that sounds like alien invasion to me, bro.
Well, there's really a couple different ways to look at how we approach everything in our world. If we look at science and technology, and modern medicine, it usually comes across as something that's rather forceful. All right, forceful. It's applying a definite force for a definite purpose, and it is not like. And if you can think in a whole different way, it's not inspiration. It's not helping someone to discover something. It is, we're going to come in here with a lever and a wrench and a machine, and we're going to do this. All right, and it usually happens at the expense of displacing nature or upsetting delicate balances of which we know little in the human body, if we're talking about certain medical processes and procedures. So that's kind of the hallmark of what we do when we build technological stuff. Is it's strong, it's direct, it gets the job done, and it's forceful. And I think that there's a significant difference between that and that whole other little fluffy subject that I broached a minute ago.
No, it was a good subject because that's the positive. That's the real positive side of it. I mean, if you could enhance that, not take over it. It's not what I'm saying. If you can enhance it, and what do I mean by enhance? If you can have a system that allows for intuitive, immersive.
We could, but the people that build this stuff need to have that in mind at all times.
Yeah, they do for themselves.
Okay.
I mean, how do you think tanks work today, man?
I don't know, really.
Right. So think tanks would benefit from this kind of technology because you'd be able to engage in advanced, intense, critical thinking with your think tank group over the course of a month, for example, and you don't really have to be in the same room in a meeting all the time. So
right.
Realistically speaking, from a privacy perspective and from a security perspective, having these kinds of technologies at the upper echelons where they would use them to engage in cross-platform and cross-skill set collaboration constructively to enhance and accelerate and improve efficiency and productivity of achieving whatever their goal is with, in this case, something in a think tank. This kind of technology is incredibly powerful because now you're not using your vocal cords and talking over a phone. Now you're not traveling around, taking your meat suit from point A to point B along with everybody else who's getting together in this think tank, because that could be a problem if you have, people that might be, not working for your government who happen to be living in your country and might be looking at these people because of what they do on their the rest of the time, right? What do they do in their professional life outside of being part of these upper echelon think tanks, right? So a lot of this technology is very, very applicable for diplomacy would be another great example. Diplomacy. Why fly across the world when you can just log in, have a discussion, and enjoy each other's company and move on?
Yep.
I mean, that's
much
really
more efficient, much more direct, less chance for error or misinterpretation.
Yeah. I'm gonna show you some of this stuff here. Nanoparticles for use for enhancing brain performance or for treating stress. Nanobiotics, this is 2017 patent, and show you some pictures before I show you the highlights out of this patent. Look, cathode stimulation creates an inhibitory effect on neurons, and anode stimulation, right? So a DC circuit, positive, negative, anode, cathode, with nanotech in your brain to do things like turn off parts of your brain or excite parts of your brain with nanotech.
Yep.
Let's see.
Polarize and depolarize axons specifically.
Right. And that's exactly what they're saying here. Hyperpolarization, depolarization. It's a skull, anode, cathode, right? Just thinking around. Anode, cathode, putting patches on your head to run current through it. Just giving you addition of nanoparticle suspensions, nanoparticle groups.
Suspensions.
And so it's just, they go through, this is pulses of energy, and it's applicable. I think you should see this, because when you start looking at how like ultra wideband, when they graph out the pulses for ultra wideband, or they graph out pulsing for different types of modulation schemes, it's kind of like this. I almost don't want to whisper anymore because Biden kind of jacked that up. What a douche. Anyway, let's look at the highlights of this one before we move on. And nanoparticles, right, enhance the excitatory or inhibitory effect of an applied electric field. So you have an electric field that's applied to your body or your brain that then works with the nanoparticles to enhance the way that the electricity is working on your nervous system in your brain. Nanoparticles or aggregates, right, allow for the decrease of applied current, which means if you have nanoparticles in your body that are responsive to electricity, it now does not take as much electricity to do what used to take a lot. So what does this mean? Well, now maybe I don't have to have electrodes directly on your head. Maybe now I could have, 6 or 8 antennas within 5 feet of you, or 10 feet of you, or 30 feet of you, that can generate the electric field at a much lower and FCC compliant field strength, and it still interacts with your nervous system and your brain.
Well, you know what great antennas, tiny carbon nanotubes, which are very conductive, would be, and that they're working with the material science to build those things. Now, having those be at a specific length, tuned to specific frequencies, wouldn't be out of the question. And
no, not at all.
Very small.
And it would create an opportunity for some type of an interface. It might not be bidirectional. It might only be simplex and not duplex.
Yep, true.
And also what it would do is allow for a re-resonance. So if you can resonate the carbon nanotubes, as the carbon nanotubes start resonating, it's true for just about anything else, it in itself has its own energy field now that has unique characteristics nearby.
Right.
And so what we're getting at here basically is this idea of transducing, exchanging one form of energy for another. And when you start looking at carbon nanotubes, because you brought it up, when you look at carbon nanotubes and you mix them with other things, you can start creating complex energy exchanges where light will convert to electricity, or pressure or sound will convert to magnetism or to light.
Just to bring it to something practical in graphic terms, the typical neuron, brain neuron, for example, case in point, would have multiple dendrites, which are inputs, and usually one axon, which is an output. And imagine straddling a tiny carbon nanotube right alongside an axon, and then being able to activate, to resonate that thing, to create a net charge differential. And this is all sort of well within the range of what could be done now, and create a charge potential that's either going to inhibit or activate that axon. Even if the neuron wanted to fire, it could be blocked from going down the axon by that interaction.
So it says here, in a typical aspect, nanoparticles aggregate, right? And they're used, check it out, they use them for enhancing physical performance or for enhancing cognitive performance. For example, learning, memorizing, sense perception, the perception of sense. Sense perception, wow. What does that mean? Sight, wow. Taste, touch, smell, and hearing. enhances attention or decision-making of the subject. Now, bear in mind, earlier we were looking at the pictures for this patent, that these are extracts out of this patent for enhancing brain performance. They also talked about being able to turn off parts of the brain.
Do you guys get an inkling of how far ahead this stuff really is? I mean, this is, this is
function.
This is patents here.
Enhancement of physical performances is one exciting application for improving brain functionality by stimulating specific areas of the motor cortex, increase of fine motor skills. You're going to be a sashimi sushi making MFA, and you've never made sushi before. Application for improving brain functionality by stimulating specific areas of the motor cortex. It increases fine motor skills, as well as modulating gross motor properties such as fatigue and explosiveness, has been demonstrated in human subjects. So you can induce fatigue and make somebody incredibly exhausted. That doesn't sound like a lot.
Or you can mitigate their explosiveness.
Or you can make them explosive. So what does that mean? I'm waiting. All of a sudden, my objective is
boom,
2 feet away from me. Out I come. Guns ablazing, hands ablazing, knives ablazing, whatever. And it's going to be as badass as I can be with the help of AI.
And then on the other side, the fine motor skills. Imagine a fine old school Swiss watchmaker making small watches with little tiny parts and having fine motor skills. Perhaps a person that never had those fine motor skills before, and they'd shake like a leaf, but they'd be able to do such a thing as that.
Here's an example. You got a guy he's your driver, and you're in a crew or team, and he's your driver, and his job is to drive. Even if he's banged up, he's driving because the other guys have their jobs to do, like navigate and run the radio and shoot back, for example. What happens if he's injured? What happens if he got shot?
Keep him running. Keep him running.
Sick, or all of a sudden, like he can't function anymore. You can have this tech inside your soldiers, and AI just kind of takes over and artificially overdrives and stimulates the eyes, overdrives and stimulates the hands and the feet, and can help assist the meat suit function while driving
absolutely
a sandrail, for example, that's got gun mounts on it and 4 or 5 guys trying to get away. And the guy's bleeding out, and you don't have time to stop and fix him. So you do what you can to control the bleeding, but he's weak now because maybe he lost, half a gallon, couple pints, half a gallon would be a lot. And now he is not able to respond. He can't turn as fast. He can't shift as fast. His brain does not process the 300 yards ahead and 200 yards ahead, 100 yards ahead in order to expertly navigate where they need to go so they don't break their car and ultimately not make it out, right?
Yeah, but in that case, that's absolutely good because let's say, he gets shot in one arm and now he doesn't need both arms to drive the vehicle, but that by way of controlled constriction of the muscles in that arm can reduce the outflow of vital bodily fluids, for lack of a better word, and the guy can manage, basically artificially just patch the guy up until they get out of danger.
Yeah. So nanoparticle construction, it gets into this stuff, and you can look at what these different chemical abbreviations mean, but it's not all exclusive to iron oxide nanoparticles. So
it isn't.
A lot of talk out there right now about spions, which is great because it's a very well studied science because it's useful in therapy treatments for especially something like cancer. And then when you start looking at advanced genetic therapies outside of cancer, using iron oxide nanoparticles are useful because you can steer them around in the body. And so it allows the medical applications to be less elegant, if you will, versus a therapeutic that's got genetic markers and other biomarkers to when it's inserted into the body. Just through the elegance and the sophistication of the construction of the biologic material will make its way where it needs to go. It will disassemble and disintegrate and reassemble as it's supposed to, all with genetic information and other biomolecular compounds, right? That's very elegant. A less elegant way would be the application of iron oxide nanoparticles or other paramagnetic nanoparticles to do the delivery.
Yeah, but it's implied in the bold, right where you are in that bold print sentence right there. Organic nanoparticle prepared from a conductor material is typically prepared in conjunction with an organic material. And it's a whole lot more than just the paramagnetically active molecule. The preferred organic materials could be selected from polyaniline, polypyrrole, polyacetylene, polythiophene, polycarbazole, polypyrene, and poly-3,4-ethylene dioxythiophene, and or poly-3,4-ethylene dioxythiophene, polystyrene sulfonate.
I don't know what any of that shit means, Indy.
Lots of different in the panorama of available chemicals, they can pick the ones that are going to be the least antagonistic to the cells that they're going to be around. And meanwhile, at the same time, having incorporated in that the conductor material, which is up in the bold print topic sentence up above.
Mm-hmm.
Yep.
Nanoparticles prepared from semiconductors, intrinsic semiconductors, right? Semiconductors. So these don't freely allow energy to flow through it.
Semiconductor typically would be referred to as a switch of some sort. And we looked at some biological analogous diagrams of what were silicon switches, but made of biomolecules. Typically, it's an input, an output, and a gate. That's usually what makes a semiconductor, that like a transistor or a field effect transistor.
So for those of you that are interested, periodic table element from the group, looks like group 4. Right?
Silicon and germanium, sure.
Silicon, germanium, you have in here, looks like aluminum. There's gallium in here, which is a huge deal. Gallium nitride and other forms of gallium are useful for software-defined radios. There's a lot of research being done with gallium nitride and other gallium composites because of its ability to work very well with being able to scale radios, the frequency of radios, amongst many other things. It also allows for rapid charging. A lot of the more expensive chargers now, they're starting to use gallium in their construction, in the materials inside, because it just works better than aluminum.
What's really neat is they're experimenting with all these different types of compounds. And yeah, you've got gallium and silicon, but you've also got zinc selenite, zinc tellerite, cadmium tellerite, a whole lot of compounds there that they're going to be able to go through these and see which ones give them the properties that they want.
Yeah. Nanoparticles prepared from an insulator having a high relative dielectric constant, relative permittivity, right? So what I'm getting at here, this is like the first one. It's just the first one of a few that we're going to look at. What we're getting at here is that the nanoparticle assemblies are not exclusive to iron oxide nanoparticles. And
right.
The more that you look at medical patents that deal with nanotechnology in the brain, you find biocompatible polymers, and you find things like this, where the nanoparticles that are in use are designed for a very specific purpose so that only specifically applied energies or specifically applied perturbations or changes in the biological organism
and they'll also design them to have specific frequency capabilities as well. Go back up just a little bit there for a second. I know what I was going to say. So yeah, selecting materials based on dielectrics, which are insulators, and they can sometimes be used to store charge, as well as conductors, and a combining of which conductor you want to use and which insulator you want to use in a particular application with a particular size and with a particular set of conductivity and frequency resonance characteristics for what you want to do. There's huge work going on. I'm amazed at how much work is going on in this area.
Nanoparticles or nanoparticle aggregate shape. So the shape has a lot to do with nanoparticle construction and nanoparticle function. The dimensions, as well as the mass, all of it, and what it's actually made out of, have everything to do with the way it interacts in its environment. Huge deal with construction. And that's where, when you start looking at schools like Harvard and MIT, especially MIT, some of their fabrication techniques are remarkable, and that's just what that school does. That school makes tools for other people to make really cool stuff. That's what they do. So shape is another big deal, as well as composition. Biocompatible coatings. So I'm not going to go through all of the biocompatible coatings, but what's important here is that when you start looking at what biocompatibility looks like, a lot of the prefixes and suffixes for what these chemical compounds are, you're going to find them in just about any ingredient list when you go to your local pharmacy to pick up things like lotion, soap, deodorant, shampoo, smell good perfume, you name it. All of the biocompatible particles, biocompatible coatings, biocompatible compounds, right? That's the pool they choose from, folks, as well as the food generally recognized as safe list, the GRAS list, generally recognized as safe through the FDA. That is also another list that would contain chemicals and compounds that are generally recognized as safe, meaning they're biocompatible, that if they didn't in fact break down for some period of time, might be useful to do something like wrap around a compound that's toxic to the body.
Yep.
So this is a huge deal. Biocompatible coatings are huge. It's huge when you start looking at putting complex nanotechnology together so that it does a few things or many things once it's delivered where it needs to go. And we're not going to get into all the different, like I said, all the different pieces here, but if you're ever curious, you can look this stuff up on the spreadsheet and take a couple pictures at your local pharmacy with all the deodorant, soaps, whatever, and just start looking around and seeing what's kind of the same. You might find things that freak you out. It freaked me out, I'll tell you that much. Biocompatible coatings allow, right, nanoparticle stability in fluid, such as physiological fluids. So biocompatible stability in blood, plasma, serum, anything that's fluid, or any isotonic medium.
Always going to be important, as well as making sure that they don't have something about them that triggers the immune system to go in and engulf them and get rid of them.
Right. Okay. Compositions of nanoparticles. Again, this is for enhancing brain performance and for treating stress. This is just the first one. I'm kind of long-winded on this one, but it's important, right? They can be in the form of a solid, a liquid, particles in a suspension, an aerosol, a gel, a paste, and alike. Preferred compositions are in a liquid or a gel.
Imagine an inhaled aerosol, right? The lungs absorb stuff very easily. Imagine an inhaled aerosol.
Yeah, you tell me how many things you use on a daily basis that come in the form of a solid, a liquid, a gas, a gel, a paste, or just anyway. We are so far in the future, folks, and where we're going.
Just as a side note, this is a little digression, but there's a little article that I was reading, and I won't put it up in the show, but the manufacture of artificially designed nanoparticles and the ability and the propensity that those things have to diffuse and disperse out into the environment, like out into the dirt, into the water supply, and to try to filter those things out. They're so small and they can spread around. It's like, you really don't want to make a whole lot of this stuff. And the article that I was reading about people that are concerned about when these things start to just, we always have waste. We always have stuff that gets thrown away. We always have stuff where the vial falls on the floor. Okay. I mean, in a lab, the vial falls on the floor. It dribbles down the drain. The drain goes out into the sewer disposal system. And there you go. There's a whole bunch of little nanoparticles that weren't supposed to get out. Getting those things back, especially if they were designed with some particular agency of their own, that they were designed for, really hard. And what could happen, it's not, it's that, once again, this is for entertainment purposes here, but I mean, the potential for an accident to happen And for something that was designed, which could be a little bit dangerous in the wrong environment, to get out there is not something to brush off. That's all I wanted to say on that mini rant.
Yeah. So check this out. The composition, nanoparticle composition that's designed to be delivered to the body to enhance your brain or treat stress can also have stabilizers, sweeteners, surfactants, polymers, and the like. Sweeteners, that's interesting. What does that mean?
Tasty. People are going to want it.
Want to consume it. Stabilizers. Yep. Well, stabilizers come in all kinds of processed foods, so God only knows what's generally recognized as safe that's also biocompatible. Yep. Surfactants.
Surfactants are things that lower surface tension, usually for the purpose of causing greater, faster absorbability.
And you have polymers. So when you look at polymers and you look at hydrolyzers, things that hydrate your skin and hydrate your hair and all that, a lot of that's polymers, folks. A lot of it. So it can be formulated, the nanotech that you're going to use to stim your brain and help with stress. It can be formulated as an ampule, an aerosol. It can be put in a bottle. It can be in the form of a tablet, a capsule. By using techniques of pharmaceutical formulation that are known by people skilled in the art. So it can be administered to a subject. Nanoparticles can be administered to a subject using different possible routes.
Intracranial.
Straight through the brain, right through the skull, straight to the brain.
Whoa.
Intravenous, right? So that's like IV. Saline solution is a good visualization for what an IV is, albeit I wonder what's in that stuff. Saline solution, I mean. Airways, right? So inhalation, intrathecal.
I don't know what that is. I wonder what intrathecal is. I'm going to look it up.
Okay. Intraocular, so through the eye, or oral, right? So you can, by mouth, swallow. Preferably using intracranial or intrathecal. So we got to look up what intrathecal is.
I'm getting it.
Okay. Repeated injections or administrations of nanoparticles can be performed as appropriate. It says that this stuff can be used typically for an animal, preferably a mammal, even more preferably a human. Doesn't matter the age or the sex.
Okay, so intrathecal is introduced into or occurring in the space under the arachnoid membrane of the brain or spinal column. That's intrathecal. So rather than directly, putting a needle right into somebody's head, it's in the area under the brain or at the base of the spine, at the top of the spinal cord.
Got it.
That's okay. We got that.
So here's the next one. And I'm going to show you some pictures. We kind of spent time on the last one to lay the foundation of what's generally looked at as possible. And so here we're going to get into some really cool, interesting stuff. We'll breeze through it. University of Chicago and the Department of the Navy back in 2012. Delivery of nanoparticles to neurons. Neurons will be in your gut, in your nervous system, your
there's a lot of them in your heart,
in your brain, in your heart. You got it.
There are more neurons in your heart than there are heart muscle cells. Matter of fact,
there are neurons in every single organ of your body because that's how that organ talks to the brain and to the rest of the body. So when you talk about neurons, it's everywhere in your body. Neurons aren't exclusive to the brain. And again, going back to the DARPA programs, when you start looking at their haptics program and all these other things that are designed to interface with the nervous system, right? Now it kind of maybe, hopefully, starting to make sense where you can deliver nanoparticles to neurons, which are just single cells that comprise or make up a nervous system, all the way up to including the sensors, the nerve cells that are in and around your organ systems so that your body talks and knows when something's right, when something's wrong, etc. And here it talks about using peptides attached to nanoparticles, in this case, quantum dots, selectively directing nanoparticles to neurons in a tissue or an organism. So what does this mean? This means that a particular biomolecule that has a target in the body is attached to something like a quantum dot so that it will go to a specific tissue in the organism and then deposit. And what you have here is a nanoparticle that's a quantum dot. It's a multi-layered quantum dot, which means that, I'll leave it there. It's a multi-layered quantum dot without getting into the specifics of what CDSE and zinc whatever do. Typically what this is a transducer. So sound, for example, might be introduced to this nanoparticle, and it would then elicit a photon of light, or it will elicit a magnetic field, or it'll heat up, or whatever, right?
It could develop a charge, an electrical charge.
Right. And exactly. So I got to move this little bar out of the way.
If you build something that has the right combination of ions and then you mechanically vibrate it or agitate it, it can start to develop electric charge. I mean, that in macroscopic scale, that's the way generators work. It's designed, it's got wires in it, but you apply mechanical input into it, and then all of a sudden you're starting to get electricity out of it.
So here's where it gets weird. Quantum dots elicit specific wavelengths of light based on how they're made. So if you can target where these quantum dots go, particularly in the brain or in the nervous system, and you have optogenetics involved, you could theoretically deliver optogenetic therapy to the eye or the brain or whatever. Right?
Absolutely.
And have the right opsin be applied, which is just a fancy term for a channel that's put into the membrane so that it responds to light. It's a protein channel that opens and closes based on light shining on it. And it's specific enough where you can pick a particular opsin, a particular compound, protein compound, and deliver it, and it will only respond to, for example, 500 nanometer wavelength light, or 550 nanometer wavelength light, or 600 nanometer wavelength light. And so the point is this: if you can excite a quantum dot that has many layers with something like electromagnetic energy, with something like heat, with something like ultrasound, and then once it's excited, get it to emit or
certain wavelength
photons of light of a particular wavelength that happen to be the right wavelength for something like optogenetic control of the brain.
Exactly.
Why you don't need wires anymore? You don't need any of it anymore. You just need something that, put it in a freaking candy bar and, give it to your kid. Have a nice day.
All you have to do is to have designed that thing the right way and get it parked in the right place.
Yeah. So here's an example. We're applying voltage or something, and it's creating a reaction. And so here's where it gets cool. You can make quantum dots, or you can make nanotech as little assembly mechanisms where it's like the cornerstone of the foundation. So you can excite this thing, and it can be doped with particular peptides or other biomolecules. And once you excite it, it changes, like you said, Indy, which was a great term. It changes the charge, and now all of a sudden different peptides, different biomolecules start attaching to what you've delivered to the body, and you start building construction materials inside cells, in between cells, whatever. And it's biochemistry with material sciences that do things like convert different forms of energy from one to another at the quantum scale, at the nano scale. And so like I said, we're
it's transducing. You're essentially making it a transducer. A transducer takes one form of energy input and transduces it into a different type of energy output.
Here's an actual picture of a quantum dot with a polyethylene glycol coating with palmatic acid groups, which, interestingly enough, are biocompatible, acid, right? When you start looking at what the compounds are and all the cosmetics and crap that we slather all over our bodies and stuff that we eat from the store, these things, this is where biochemistry comes into play here, folks, and why these technologies are, in my view, distributed across a wide variety of industries and corporations, because you could potentially have Johnson & Johnson or Procter & Gamble, for example, deliver the different biocompatible components through the different things that you would buy from them, like toothpaste, deodorant, soap.
These things are really small. They're really tiny. They could be incorporated into many products, and you wouldn't even know that they are there.
These are binary systems, in my view. Binary systems, and the sophistication. Go as far as you want with what you think is possible. That's completely up to you. What I'm telling you and what I'm trying to explain to you is the concept, trying to conceptualize you going through your day, and you eat and you drink and you bathe and you put things on your body, and you take medications, you take supplementation, whatever. And over the course of a day, a week, a month, you have introduced foreign materials into your body, albeit you probably think it's all really, really good for you, but do you really even know?
And polyethylene glycol, PEG, is a very common component in a lot of, creams and lotions and things like that. Very, very common. It's either that exact one or because they're calling it PEG 600. Yeah. But that general family of compounds are extremely common. So the idea of encapsulating a quantum dot inside a piece of something that's already a whole lot like what's in many, many consumer products now isn't a stretch at all.
No, they use
it's entertaining.
Glycol in food, also.
Yeah.
Anyway, let's see if there's any interesting highlights out of here.
That looked interesting.
To the next one.
Okay.
Quantum dot, capable of emitting electromagnetic radiation. Quantum dot is luminescent. The quantum dot includes a core of one or more first semiconductor materials and may be surrounded by a shell of a second semiconductor material.
Yep.
Quantum dot core may be a semiconductor shell referred to as a core shell quantum dot. The surrounding shell material will preferably have a band gap energy that's larger than the band gap energy of the core material and may be chosen to have an atomic spacing close to that of the core substrate. So what this really means is the band gap energy larger than the band gap energy of a core material. So you're able to regulate when this thing discharges, which means it's not going to be a 1-to-1 ratio. You're going to have to, for example, apply a few different photons or pulses of energy or perturbations, whatever you want to call it, a few of them to get the quantum dot to elicit a photon or a perturbation of its own through transduction. And so very, very sophisticated stuff. Quantum dot, surrounded by a coat of organic capping agents. So we looked at all the pictures, and these are the words that support all the pictures straight out of patents. It's copy pasted out of patents, and I've got some of these highlighted, and we're just going to look at some of the highlights. So quantum dots, as well as other nanoparticles, may be biofunctionalized for use, for example, in vivo, in the body, in tissues, and as cellular labeling, cellular labels. Why would you want to label cells other than to maybe understand where they are with respect to other cells? Can you imagine labeling the neurons, the neural cells in your brain? Did you know that AT&T holds a patent to be able to map and network down to a single cell in your brain?
Yeah, well, the first step is to label them, and then the second step is to address them individually. Go
down the road of infinity to tomorrow. I'm being stupid by saying that, but really, this stuff has been in motion for a very, very, very long time. The patent with AT&T I'm referring to was originally filed in 2012, or it was granted, in 2012. Discussing networking and routing biological hosts, which means they subnet your hands, your legs, your muscles, your eyes, your brain, your neural circuits, all the way down to fingers, toes, down to a single cell. And then they use something like your phone to run communications to the different network locations in your body, just like your router does to the different phones and televisions and connected stuff you have in your house, only it's down to a single cell in your body. This was patented back in 2012, publicly.
Just like the internet works, right down to a specific IP.
Right.
To a specific machine.
Right. Development of biological labels based on quantum dot probes and biosensor development. Other uses of the biofunctionalized materials may include protein ordering for molecular electronics, where quantum dots could serve as fluorophores, which is just, they light up, they illuminate, and electronic components, energy harvesting, quantum dot barcoding with quantum dots, barcoding. And drug discovery assays, where the fluorescent properties of quantum dots may be combined with bioactive peptides, blah, 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 blah.
All right there in black and white from 9 years ago.
Yeah, it's been a long time coming. Delivery of nanoparticles and or agents to cells. I want to share, this is from MIT. And I want to share something with you. I'm just going to type in remote. And what I'm going to show you in here is where it says multifunctional nanoparticles are multivalent and can be remotely actuated and imaged non-invasively. Superparamagnetic nanoparticles embedded in tissue, superparamagnetic nanoparticles embedded in tissue transduce external electromagnetic energy to heat, thereby melting the oligonucleotide duplexes and act as a heat-liable tether to model drugs. So all that said, what they're getting at here in this one example of remote actuation of superparamagnetic nanoparticles is to generate heat so that the bonds that are made with the paramagnetic nanoparticles and the medicine, right, the oligonucleotide, the genetic information, the whatever, the bonds melt. They are heat sensitive. So you can excite the magnetic nanoparticle, putting it through an oscillating field to generate heat, and then it will break those bonds. And that is a remote trigger to actually get something to happen once the medicine is embedded in the tissue. Embedded in the tissue. Let's look at what the next remote says. Remote monitoring of protease activation. Don't know what that really means. I'm not a biology guy, but if they can do it with protease, can they do it with glucose? Can they do it with oxygen? What about nitrous oxide?
A protease is an enzyme that splits a protein apart into its component amino acids.
Beautiful. Remote monitoring of subcellular functions is what I'm hearing from Indy. And multifunctional nanoparticles are multivalent, can be remotely actuated, imaged in vivo. We've already been through this. This is a repeat. Remotely triggered release from heatable surfaces. So this is using electromagnetic fields to remotely trigger activation of something else, some remote trigger, right? Based on heat, generating heat. Here's examples of it in this patent. Anyway. You get the idea, right? Remote activation. Let's move on. This one is from Battelle, and this is their actual patent from that N3 program that we looked at so many times, where they're delivering magnetoelectric nanoparticles.
This is the thing that should literally floor everybody. This is patented, documented, researched, being developed at various levels of material science. That should floor everybody.
A method of administering a drug into the brain of a mammal, human or non-human, is described. They're administering a drug, not the nanoparticles themselves, the magnetoelectric nanoparticles. It's that and a drug. I'll read further. In this method, the magnetoelectric nanoparticles and a drug, which could be a therapeutic, up to and including genetic information, up to including something that modifies your body to potentially, for your entertainment, offer an input-output interface that builds a proverbial Wi-Fi chip. I'm just saying, but it's for your entertainment. Not saying that DARPA is actively working on a bidirectional interface with a company like Battelle and Rice University and others to pair up these magnetoelectric nanoparticles with genetic information that will go into the brain and allow for the creation of a bidirectional interface. If you were here last show and the show before, we looked at that in some detail. So in this patent, just in the abstract, it states that this is what this can do. And Battelle is now in phase 2 of their 3-phase trial to make this a reality. Let's see if there's anything in here that is fun and interesting. And it is. Here we go. Applying a non-alternating or a slowly alternating, right, magnetic field so that you avoid heating, so less than 40 kilohertz. And if we ever get far enough to look at what the coil antennas can do and the proximity sensors can do in your phone, you will find that these ranges are well within what a software-defined radio can do when you turn it on and run through your coil or coils or other antennas in your mobile devices. They can emit these frequencies and these fields, folks. And so can your power lines in your house, because it says here 40 kilohertz, preferably less than 10 kilohertz or less than 1 kilohertz or less than 50 kilohertz. An electric or a magnetic field, right? So when you start looking at FCC requirements for what's an acceptable electric field and what's an acceptable magnetic field, the only thing it really stops is the heating of tissue, right? And what is going to be understood or felt as a shock. Like if you get into an electric field that's over 614 volts, right? You're going to feel a shock. You're going to actually feel it. It's going to feel like you got shocked. And it's a lot of power to do that, but that's really all the regulation there is. And I'm simplifying that immensely, but the sophistication of these technologies, bear in mind, the first patent we looked at talked about administering magnetic nanoparticles so that you don't have to use strong electric fields anymore. You can use a much weaker electric field and have the same thing happen.
Yeah.
And so the question really then becomes how sensitive can we get with something like a cell phone? And how powerful can we get with something like a cell phone? Because the cell phone manufacturers, in order to quote unquote comply with the safety requirements from the FCC or other organizations globally, right? They have to be able to scale up and scale down their power. They have to be able to change the way they modulate their antennas in order to comply. And so what that means is that there is software and connectivity to a mobile device to scale and change the power that is emitted from the antennas and to scale and change the frequencies that are emitted under the guise of safety. And I want to illustrate something for you as plainly as I can. Just about everything that gets codified into law for your quote unquote safety, generally you should look at that again and try to understand what the meaning is behind it. Because the way that new technology is going to come online and be infused and forced into our environment will be under the guise of safety. And as a result of that, once it's implemented, because now it is implemented as a requirement to make sure you're safe, you cannot remove it. And in fact, it may be illegal to even contest the safety efficacy once it's been deemed safe.
Man, that's, that really makes me think. I'm sure it's making everybody think.
So it says here it's not necessary that these magnetoelectric nanoparticles, they don't have to pass into the brain. However, it says preferably the mass percent of the drug passing into the brain.
Yeah, I read that ahead of you. And it seems like they've got word salad going in there.
Exactly right. They want legalese to offer the ability for this company to sue somebody for stealing their intellectual property, but at the same time, it's written in a way that they can defend themselves.
That's right.
From any type of a suit saying, "Hey, man, this is not good," or something you did is wrong, or you stole property. Right. So.
We're covered. Nothing to see here, folks. Drop the lawsuit.
COFE2O4. Barium.
Cobalt iron oxide?
Very, very common. Magnetoelectric nanoparticles don't have to be iron oxide, folks. It could be
Cobalt.
COFE2O4, which is,
Cobalt iron oxide.
Yeah. Just going to leave that alone there. So one advantage of this approach.
Titanium oxide.
Right. Yeah. So.
Did the word barium ring a bell with anybody? We've heard about barium. I'm not going to say any more. We're just entertaining you here. But we've heard a lot about barium showing up in unusual places overhead.
We need to combat climate change. Effective programs.
Killing me.
Stratospheric aerosol injections.
Oh, no.
And we estimate that approximately $10 billion a year will provide an effective stratospheric aerosol injection
much safer to use chalk dust. Come on, TMC.
Brennan. Anyway, so a third advantage is that the nanoparticles to be used have high biocompatibility, and the strength of the magnetic electric fields to be employed will be lower than that used for transcranial direct current stimulation or transcranial magnetic stimulation used for blood-brain barrier disruption in this patent. Note to self, come back later and look at this. In some embodiments of the invention, a magnetic field of less than 1 Tesla or less than half a Tesla. In some embodiments, a field in the range of 0.001 Tesla is applied. That would be what, a micro Tesla?
Zero. How many zeros? I was just typing to somebody. 0.001.
Is that a micro Tesla?
That's a millitesla.
That's a millitesla. So that is down to 1 Gauss. A millitesla is 1 Gauss. And 1 Gauss is a measurement that is the same as the Earth's magnetic field. The Earth's magnetic field, on average, is about 1 Gauss. That's how it got 1 Gauss, right? 1 Gauss, 1 millitesla. So a magnetic field equivalent to the Earth's magnetic field is an effective enough field to deliver biocompatible compounds into the brain. I'm just saying.
Yeah.
It's right here.
Not real strong. Just takes a little bit.
So you tell me if something like your phone can emit an electric or a magnetic field, excuse me.
Way plenty more. Way more than that.
You got it. And round we go.
We could pull up an engineering conversion table, but the phone radiates in the range of, a couple hundred milliwatts on average. That's a lot.
Yeah. And when you start looking at pulse modulation and creating net biased electric fields, and net biased magnetic fields, sky, you can create an artificial electromagnetic environment, have a net biased field, and then inject pulse modulation that modulates the net biased field.
Right.
And this is where the smart grid and your smart meter on your house, this is where this is how this is going to be done, folks. This is how this is going to be done on a massive scale, in my entertainment only opinion.
It can be. You can speculate
fields in your house and then introducing pulsed modulation through things like your home network system, your Wi-Fi router, your connected car, your connected phone, your connected thermostat, introducing pulsed modulation in a net biased AC field from something like your home power lines, and you'll be able to get very sophisticated directed magnetic fields to go get your booster, homie. It's going to be good for you.
And just because these things can be done doesn't mean that they will, but one would need to, in intellectual honesty to oneself, one would need to ask, do I know what they're doing? If your answer to that is no, then your eyes need to stay peeled. And then, are you in control of it, or is someone else in control of it? And, those two things would tell you that you need to be vigilant about this kind of thing.
So here's some examples of magnetic nanoparticles. So it doesn't stop at iron oxide. Spions, great. Research the hell out of it. You'll find all kinds of cool stuff they can do with spions. It doesn't stop there. You have compounds galore just here as examples. These are just examples. And it says here that
look at that next paragraph. That's really good.
It says the magnetoelectric nanoparticles can be functionalized with a ligand or a ligand for targeting cell surface receptors on the basically on the blood-facing side of the blood-brain barrier. So they can target specific locations in the blood-brain barrier based on what ligands they attach. The receptors include, but aren't limited to, all of these things: transferrin, insulin, melanotransferrin, LDL, leptin, thiamine, glutathione.
The idea of that is the outward-facing side of an endothelial cell is the one that they've designed this thing to be receptive to. So it's looking out, and it's looking out at the blood flow around it. And one of these little guys, one of these MENP, comes tootling along and says, hey, here I am coming down the bloodstream. And, oh, look at you. Yeah, I like the outside of your endothelium. And guess what? I have a ligand on there that's made to just mate up with you like a lock and key. So here I come. That's kind of what it is.
The functionalized magnetoelectric nanoparticles can be administered non-invasively through an injection, and will have the ability to find its way onto the blood-brain barrier endothelium and bind to these endothelial cells. And listen to this piece. In another embodiment, the magnetoelectric nanoparticles can be guided to the brain through the use of a DC magnetic field. And the way you get a DC magnetic field is by using an alternating magnetic field, something like your home power line,
to create a DC potential.
And you create a net biased field.
That's right.
So you still have an AC interaction going, but when you look at the far field characteristics of that electromagnetics, it is a net DC, delta. It reads as a DC bias.
That's right. Exactly right. And the best embodiment of all would be to combine these two functionalities. And when we're talking BBB, we're talking about target is the blood-brain barrier. So
the magnetic field will induce magnetoelectric coupling in the magnetoelectric nanoparticles, which will in turn create an electric dipole field or an electric potential, meaning a voltage. So check this out. When these things get to the blood-brain barrier and they land in the endothelium cells, they can stimulate the magnetoelectric particles and generate a voltage, which then disrupts the tight junction proteins that make up the blood-brain barrier.
Right, to allow permeability.
That's right.
That's right.
Once the blood-brain barrier is disrupted, drugs can permeate to the brain, right? It has been shown that an electric field on the order of 125 to 250 volts per meter is needed. Now, if you were to look up the electric field of something like an electric stove, you would be at the 250 plus 200 to 250 plus volts per meter. When you're standing there stirring the freaking SpaghettiOs, you're standing in a 200 plus volt per meter electric field.
I didn't know that. Is that right? You know that? Okay.
I do.
All right. Plus, you just made me hungry, but that's beside the point.
Should we? Let's
SpaghettiOs. Now I'm on SpaghettiOs. Done.
ELECT, electric field of electric stove. Electric field of an electric stove. Let's see, EMFs from home appliances. Let's see what, and we're just going off the cuff here, right?
Yeah,
Space. How cute is that? So, non-ionized radiation.
It's all going to be non-ionizing. Yep.
Cordless phones, TVs, computers. This might not be what we want. Electric blankets.
Doesn't look like. Well, wait a minute. There was a little chart there.
Hair dryers. No, this is not the right one. I don't really want to spend a whole lot of time digging on this, but it
well, we can give everybody a little bit of homework,
We're going to come back and we'll come back to that.
Yep.
Just to support what I just said. You could look it up for yourself.
Yep.
If you doubt or you want to know, but it's amazing what
all you guys, we give homework assignments,
we do.
But it's for everybody's good. Come on, learning is good. What happens to a brain if we don't use it? It's like a sponge. It dries up. We got to keep it moist.
All right. So in another embodiment, magnetoelectric nanoparticles can be loaded with drugs and can be programmed to release the drug upon magnetic electric stimulation. One way of doing this is to functionalize the magnetoelectric nanoparticles with electrical magnetic stimuli responsive polymers.
Exactly.
And encapsulate the drug in these polymer coatings for an on-demand release.
Right. That paraphrases what we started off on the episode about.
And okay, so we're going to pause here for a second because I want to show you something here.
Okay.
This idea of polymers, we'll get into it maybe in another show, but I did a thread on Dr. Langer, and Dr. Robert Langer and Bill Gates are buddies.
Oh,
and
wow.
Dr. Langer made his bones building polymers that break down with a known
predictable
timeline,
breakdowns.
Yeah. And so anyway, there's a cool article here about Dr. Langer, and it gives an interesting background on him. And we'll get into, look at these eyes on these people, man. Look at these eyes. Do these look like nice people to you? God. I don't think so. I don't know them, but I'm looking at them.
Well, he may be nearsighted.
He looks nice.
She does look nice. I'm not trying to judge people. But
yeah.
He may be near or far. I don't know whatever it is. He may have those glasses that magnify the size of the eyes. I don't know.
Here it is. So Langer, early on, right, was searching for polymers that would permit the gradual timed release of medication within the body. This is Langer when he's young and doing his thing. Other scientists had considered this idea and abandoned it and considered it impossible. This was back in the 70s, I think. Let's see, Langer, 40 colleges, or it might have been in the 80s. I don't know. Many, many decades ago is the point, right? So he tried for a long, long time. Basically, he figured it out. And this dude has received awards for, look, in 1983, International Minerals and Chemicals licensed one of this guy's patents and hired him to consult for a project using polymers to deliver animal hormones. Back in 1983.
Slow timed release for animal hormones. Okay.
Right.
Yep. Mm-hmm.
Right. So he's also looking at synthetic polymer scaffolds with living cells to create new tissues and organs in the laboratory. So it cross applies. And so, look, Jay Vicente is surgeon at Massachusetts General Hospital, interested Langer in combining three-dimensional synthetic polymer scaffolding with living cells to create new tissues. So this technology is way advanced. It's not just for drug delivery. This is how the human organism is going to be cyborged, folks.
This guy made himself, they called him the Edison of medicine at the beginning of that thing. He made himself, and he did do it. He did the work to make himself a real expert on biocompatible polymers. You know, I got to hand it to him. The guy worked hard and he got somewhere.
Oh, they're not going to show the picture of Barack Obama, huh?
As for who's going to use it, that's a different question.
Oh, it gets better. This is in Japan, I believe. No, it's Japan. And yeah, come on. Where is she? Come on.
You're waiting for a particular
I'm
graphic.
Waiting for, maybe it's not gonna, maybe this won't load right now. Let's let this marinate for a minute and see if it loads, because he's sitting with a real nice lady. So we're done with the blood-brain barrier. Battelle gonna deliver magnetoelectric nanoparticles with genetic modification to soldiers' brains so that they can talk with AI and run drones with their brain. This one here, part of the National Science Foundation, Department of Defense granted this funding for this, right? University of California discovery grant, Florida discovery grant. Magnetoelectric nanoparticles and a subject interact with the magnetic field to cause stimulation of neural networks. So using magnetoelectric nanoparticles to stimulate the brain. And this originally was filed back in 2013, folks. Magnetoelectric nanoparticles deposited in your brain with the use of an electromagnetic coil to deliver therapy. Now, should we look at, I think we will. Let's look at.
Definitely. Yep.
Let's look at these just for a second. Now, these exist in just about every mobile device on the planet.
Yep, antennas, coils.
4 years or less, right? These are antennas and wireless chargers. So let's look at this one, just because it's right next to the iPhone one. And so what you see here is a 3-planar coil system that will allow for a magnetic field to be steered left, right, forward, or back with some directionality. The more coils, the better. And Apple, for example, Apple has patents that puts hundreds, if not thousands of coils inside of a device in all of the empty space. And it's just
Thousands, really? They've gone that far with it?
Because they can vapor deposit the traces, the electrical traces, the independent wires. They can vapor deposit that stuff, and they can actually infuse it into the housing of the phone, and you don't even know that it's there. It looks like a solid contiguous piece of metal.
Yeah,
in reality, when you look down at the microscopic layer, it has been literally vapor deposited or painted. There are other ways to do it. I use vapor deposit as an example for a lot of things, but it's it's not exclusive. Vapor deposition is not the exclusive way to do this. There's a lithographic techniques and all kinds of other stuff that they can, at the nanoscale or the micro scale, literally build wires. And the example I'm giving you right now, I'll show you the patent one day. It's buried in my thousands of tabs. The entire housing of a phone, for example, could be independent wires, so to speak, that to you look like a solid piece of metal, but each one of those wires can be turned on or off. Each one of them has their own proverbial software switch, which allows for incredibly dynamic things to happen with that phone.
Right.
None of which is necessary.
Interacting combinations of various groups of those for both directionality and frequency tuning. And if you do it either lithographically or vapor deposition, you can do it with very little metal. It'd almost be invisible to you. And you really would need to look at this under a microscope.
Yeah, you're talking about like atomic layer application, where you just incredibly thin, small amounts of material at a time. So these coils are everywhere. And so anyway, we're done with the proverbial phone example. So here's magnetoelectric nanoparticles with a coil that's going to be used to stimulate the brain. And, back in 2013, and here's the different readouts, spikes and whatnot from the manipulations. And, let's see what this one says. Again, this is funded by the government in a variety of different flavors. We've talked a lot about magnetoelectric nanoparticles. So basically this is...
By the way, just as a side note, for the phone to be able to address thousands of individual little coils that are in the housing of it is nothing. The phone is addressing every single pixel on the screen to construct a picture, and in most cases, a moving picture of whatever you're looking at on the phone.
AI processor chips on a modern phone can handle like 6 billion processes at the same time. 6 billion with a B. 6 billion processes at the same time.
Yep. So the state of the art is there with the technology.
Yeah. So it says here, solution, for example, has a concentration of 3 times 10 to the 6, so 3 million nanoparticles per cubic centimeters. 3 million per cubic centimeter. They use low frequency, right? 80 hertz. So when we look at wave interference and how electromagnetic waves kind of converge into each other and they make different wave characteristics, you can get 80 hertz very easily. Here we go. Magnetoelectric nanoparticles are suspended in an aqueous solution and injected into the bloodstream of a patient. Because the magnetoelectric nanoparticles are small enough to penetrate the blood-brain barrier, they're small enough. In this case, the magnetoelectric nanoparticles are small enough to pass through the blood-brain barrier. Which means that they are also small enough to pass through capillaries. So this says injected into the bloodstream. The bloodstream could be intramuscular or subdermal.
IV,
capillaries there.
Sub-Q, it could be anyway.
You got it. And these are small enough to pass through the blood-brain barrier, which means they pass through capillaries, which puts them right into the bloodstream. And they're magnetoelectric, which means they respond to electromagnetic fields. And we've already been through how sensitive these fields can be, how low power these fields can be to start allowing interactivity with these magnetoelectric nanoparticles. And so it says here, one example, AC magnetic field, amplitude of 300 Oerstad. Anyway, you can look this up. Frequency variable between 0 and 1 kilohertz, 80 hertz, magnetic field conversion tools built in. I've added this in here if you want to look at the patent. I got a couple more, but I don't really know how much more time we have. Here's another one, nanoparticle delivery compositions. And it goes into how they're made and how they're delivered, if it'll load. Let's go back here. Targeting biologically active agents, in this case, to the central nervous system. Nanoparticle comprising some kind of metal and or a semiconductor, and a corona comprising ligands covalently linked to the core, wherein said ligands comprise a carbohydrate, an insulin, or glutathione. Interesting, huh? Interesting how easily this stuff can be added to things like food or medication. and at least one agent to be delivered into the central nervous system. Central nervous system. It says here these particles can be between 1 and 500 nanometers. Can be made of polymers, lipids, metals, and made of gold. As an example, see if there's anything in here. Yeah. So it says here, administration, right? And via a non-central route, meaning they're not going to inject it directly into your central nervous system, right? Whereby at least one agent is delivered across the blood-brain barrier to the central nervous system in association with the nanoparticle. Here it is, intracerebral, intrathecal, epidural. Suitable routes of administration also include solid or liquid composition to be ingested. So you can ingest this stuff and it's small enough to pass through the blood-brain barrier, right? You can eat it and it will go where it needs to go, in this case, up to your brain. Looks like buccal, sublabial, sublingual, by inhalation via a mucosal membrane, which we looked at earlier. What information you were given, talking about mucus in the intestine, right? Well, you have mucus in your nose, mucus in your eyes.
The idea is these things are so small that they can be absorbed practically onto any damp surface of a body.
Mucus, inhalation, genitals, rectal, skin, underneath the skin, in the muscle, in a vein, subcutaneous. It doesn't matter. It's
right.
Anybody, I mean, this is back in what, 20, let's see. Did this thing load finally? Nope. Yes. This was back in 2013 when the, looks like German version was originally filed. Back in 2013. So who freaking knows where this stuff is? And when you start looking at FDA requirements for the amount of heavy metals in food and all of that kind of stuff, this is what comes to my mind. It's like, okay, well, if you're going to allow a certain amount of toxicity in food and still consider it safe for the general public, what happens when you start adding very sophisticated nanoparticulate metallics?
Exactly. These levels are well below the safe limits, but the difference is you're going to have, let's say, a non-intelligent particle of some toxic metal, but these are intelligently designed little.
Imagine spraying this stuff on a crop, and then that crop being fed to a cow.
Absorbs it. Yep.
Right. And now it's in the cow's muscles or whatever, and off you go, right? You eat it, or you eat the plant, or you take the medication from a country, manufactured in a country made in China, right?
Yep. As long as these things can survive that whole path, that whole traveling journey.
And that, I think, is the real elegance of the science. If I were to imagine the discussions that Bill Gates would have with somebody like Dr. Robert Langer, or with Dr. Liu, you can look him up. He's an MIT guy, also works with China, or Dr. Lieber for that matter. If he was going to have conversation with these kind of people, I think the elegant piece of those types of discussions, right, what would be of interest in would be like, well, how would one go about, say, putting this into a food source? And then it would go into, well, how do we introduce it into the food supply, downstream or upstream, excuse me.
Right. Water supply reservoirs are a great way to distribute a whole lot real fast. Well, one little thing I wanted to mention is nature actually has a lot of normal mechanisms for cleansing itself. So the idea is that, designing these things is a kind of a battle between nature wanting to cleanse itself, both intra-body and extra-body, and being able to get these things to make it all the way in and either not be detected or be have such a biocompatible affinity that they're not rejected and they're not cleansed. And that would be to make them a lot like something that's already a normally occurring biomolecule to begin with.
So check this out. It says, right, this is what they made this for. This is the medical application, right? This is not like a patent that's going to specifically discuss doing the hypothetical things we're alluding to here, right? This is a medical patent that has real, tangible, real-world uses, even though it's a multi-use or a dual-use technology. Central nervous system disorder may be selected, right? So you could have brain tumors, cancer, right? That'll help with that. Neurodegenerative diseases, Alzheimer's, multiple sclerosis, Parkinson's, Huntington's disease, stroke, right? Hemorrhaging in the brain, neurological disorders, including epilepsy, infection, including viral, bacterial, or parasitic, encephalitis, which is inflammation of the central nervous system in the brain. Things like schizophrenia and depression and anxiety, genetic abnormalities, including inborn errors of metabolism, traumatic brain injury, coma, developmental and learning disorders. Putting this nanotech in the brain, they're saying, is useful to treat all kinds of stuff related to the brain and the nervous system. And I think that's it for, it's the same thing we looked at before, using ligands or carbohydrates or something that basically allows this thing to stay protected until it is released to do what it's going to do. Nanoparticles comprising semiconductor compounds, right? Same thing. Semiconductors capable of acting as quantum dots. They can absorb light, exciting electrons to higher energy levels. So this is where the science comes into play, and this idea of transduction, where you're taking one energy type and moving it into something else. And the point of showing this to you ad nauseum is to illustrate that this is not exclusive to any one school, any one company, anyone, anything. This is general intellectual property that, when deployed and distributed far enough, broadly enough, opens the door for property theft. And I think we'll leave it at property theft for now. So modified paramagnetic nanoparticles for the delivery and
knowledge out in the public sphere, hostile forces could use it to do who knows what. You can use your imagination and figure out what they might.
It's out in the public sphere for medical applications.
Stuff that's...
yeah, and when you cross-reference, so it goes like this. When you look at what's DARPA doing? Oh, DARPA wants to access your brain. Okay, well, what's that look like? Oh, well, they want to get into your nervous system, and they want to study the software that's going to ultimately interface with your biological system so that it functions seamlessly, so that we can help restore some type of a deficiency. Oh, great.
Yep.
Okay, well, what does that look like? Well, you got to start looking at contract numbers and different corporations and schools that regularly work with organizations like the National Institute of Health, DARPA, IARPA, Department of Energy, all of that. And when you do that, you will find that a lot of the stuff is revealed through the medical applications, because this is where you get to experiment. You have people that have serious problems, serious biological problems, and they're willing to do anything to improve their quality of life. So when a doctor goes to a material science / chemist and goes, hey man, I really need something that allows my patient to get up and move around because they've been bedridden for 3 years and they have bed sores. And I know that we can do better than putting a brick on the top of their head and having them do stuff. So can you work with me here? Well, I don't really understand a lot about the biology piece and the brain and this, that, fine. So the material scientist / chemist gets to go sit through multiple surgeries and have active engaging discussions with the brain surgeon, for example, on how this works. Why is the brain oscillating the way it is? Well, it jiggles and it moves and it does all these things. And well, what happens when you actually, open something up and it bleeds? How do you deal with that? So having a material scientist and a / chemist or whatever, right?
They learn.
They get to see the practical application and look at what it is, the end unit, the unit that is supposed to have the technology inside of it. They get to understand what that looks like.
And then they go back to their lab and go to work at synthesizing it.
And to understand better how the doctor would use it, deploy it, manage it, modify it, whatever. And that then becomes the scope, is how do I build a toolkit for a doctor so the doctor can determine how to use this toolkit?
Yep.
And so paramagnetic nanoparticles having external coatings, organic molecules, polymers, blood proteins. Oh, did you know that you can coat a paramagnetic nanoparticle with a blood protein? I didn't.
I didn't either.
Oleic acid, for those of you that understand biochemistry or even cosmetics. Anyway, let's see if there's anything highlighted in here, because a lot of these things are redundant. And here's this about that. You can scroll through these things, and a lot of the work's already been done for you. And you will pick up bits and pieces out of each one of these patents, and when you put all the pieces together, you get a really interesting picture of what may be possible. right? So this is the interesting piece out of this patent, right? As used herein, the term in combination. So they use the term in combination in this patent, right? It's what they're describing here is the context of the administration of a therapy to the subject. It refers to the use of more than one therapy, whether it be prophylactic or therapeutic, so to prevent or to treat. The term in combination does not restrict the order in which the therapies are given, right? First or second therapy, right? A therapy, listen to this is important. A therapy can be administered, right, prior to 1 minute, 5 minutes, 15 minutes, 30 minutes, 45 minutes, up to hours, up to weeks.
Weeks.
Up to, in this case, 12 weeks, right? Co-contaminantly with or subsequently to, for example, the same period of time,
or shorter.
You can deliver a second or a third dose of therapy up to 12 weeks later in this particular patent, right? You can administer the second therapy to a subject which has or had, in this case, susceptibility to cancer. In this case, this is a medical patent to treat cancer. But what they're getting at here is that the therapies are administered to a subject in a sequence and within a time interval such that therapies can act together.
Right. You don't get the synergistic effect until they're both present at the same time.
Binary systems in a patent that's discussing putting nanotech in your brain. Paramagnetic, now Albert Einstein College. Modified paramagnetic nanoparticles for targeted delivery of therapeutics. Back in 2014, folks. Binary systems that don't have to be administered on the same day, not even on the same week, not even in the same damn month.
Probably not even in the same year.
One wonders at this point now, almost 10 years later, right?
Yep.
If it is that delayed. I think it's true. I think it is delayed. I think this is the whole thing. Oh, interesting terms in here, being able to dry this stuff. Listen to this. One embodiment here, the making of these compounds, right? You can add fatty acids. You can sonicate, which is just using vibration in water, for example. You can dry this stuff, right? And you can make it into a powder. So anyway, it doesn't have to be in a shot. It can be in a powder form, which means it can be in a gel cap. It can be in deodorant. It could be in food. It could be in anything. It could be in anything.
Yeah, lyophilization is good for storage. And if it's necessary, you can rehydrate it, or upon absorption of it, it will naturally rehydrate and then become active again.
Right. And I think that is it for this one. I think I have one or two more, Andy. I don't know if you want to keep going or not, but
well, we got to probably save some for next episode. Actually,
there's more. We can move into the polymers and stuff too. Yeah, I'll stop here, and this is why. And we'll stop here. Compositions and their use for controlling the nervous system in vivo. This is University of Virginia.
That's a good place to start off next week.
Yeah,
going further.
Optogenetic and chemogenetic actuators are critical. This is the manipulation of action potentials and neural firing with light, and manipulation of action potentials and firing with chemicals. Optogenetics and chemogenetic actuators for deconstructing the neural correlates of behavior. Talks about the disadvantages having been overcome by synthesizing a magnetically sensitive actuator, or a magneto.
Yeah, but they've done some work in that area.
Yeah. Fused to paramagnetic proteins. Listen to this, paramagnetic proteins. So not only can they make this stuff synthetic with COFeO4 or barium or titanium or some type of a semiconductor, not only can you do that, they can actually use genetic information and make ferritin proteins that are used to interact with something like a TRPV4 ion channel, cation channel, that is responsive to heat. Magneto permits the non-invasive magnetic control over neuronal activity by showing remote stimulation of cells. And it talks about being able to measure intra or electrophysiological recordings in mice as they're moving around freely. In the body, electrophysiological recordings in freely moving mice. Now, what would the WO 2020-06-06-06 patent, what would that do with something like this? You mean you have technology that can go in and genetically modify cells to allow for remote monitoring of electrophysiological recordings in freely moving mammals? What? You mean you can remotely monitor things like my heart rate and things like how much I'm sweating and how much salt I have in my system and what my neural activity is, my electrophysiological profile as I'm freely moving about my house? Oh, nice. Nice. Magnetogenetic control of the nervous system was demonstrated using magneto, which is a term they use for the protein ferritins that they're able to grow with the right genetic material. Together, our results present magneto as a novel actuator capable of remotely controlling circuits associated with complex
behaviors,
animal behaviors, mechanisms of cellular effects directly induced by magnetic nanoparticles. There's a paper that talks about how this works, the interaction of magnetic nanoparticles. Like it's back in 2017. Plenty of other. This patent is really interesting. This is where they can take different compositions, different shapes and different materials of magnetic nanoparticles, put them in a single dose, deliver the dose, and then have a multiplex connection. And you can interact with one type of magnetic nanoparticle versus another based on the orientation of the magnetic field, the frequency of the magnetic field. And